Hey, thank you very much. So I get this my cue to start. So yeah, the talk is called Local Persistence of Lagrangian Intersections, which might not be the sexiest title for this talk, but it's the motivating question somehow of what I'm going to present. So I decided to call it like this. So this is joint work. It started as joint work with Jean-Philippe Chassé, and it ended as a joint work with Jean-Philippe Chassé, and also Marcelo Atallah and Egor Shelukhin. So let me now explain the problem. So the main character will be a close connected Lagrangian of a symplectic manifold, and so the symplectic manifold can be closed or open. This we don't require anything there. And then we're going to be interested in some remarkable sets of Lagrangians, right? So what's going to appear a lot is the Hamiltonian orbit of L, right? So now L is a Lagrangian which is fixed. So Hamiltonian orbit, I mean the image of L by any Hamiltonian diffeomorphism, the symplectic orbit, the image of L by any symplectomorphism. Or here I wrote sim zeros, that is like the connected component of the identity. And then there will be other sets which I will introduce later. But you see, I mean, with this notation I'm trying to get, it's the set of Lagrangians which are isotopic to L via Lagrangian isotopy. Okay, so we'll have a couple of sets like this, and the main question is to understand their topological properties. Yeah. Okay, so that's easy enough. So, so the first question would be a question about existence of neighborhoods of L where you have some path connectedness property, right? So more precisely, L again is a fixed Lagrangian, and we wonder if it admits a neighborhood U such that if you have another Lagrangian which is in the Hamiltonian orbit of L inside the manifold, right? If L prime is included in U completely, then there exists another Hamiltonian isotopy which pushes L to L prime, and such that the Lagrangian trace, if you will, stays inside the neighborhood, right? So it's really a question of path connectedness, right? So you have L which is fixed, and you're wondering if there exists such a gray open set such that if L prime is in there, then you will find another, Hamiltonian isotopy from L to L prime, which is inside U. So motivation for this question, or at least, I have at least two motivations for this question. The first one is that I really wanted to use this property, and that's a good motivation for trying to prove it. And the second one comes from the Hamiltonian setting, right? So you do have the same question. So you take the identity and you wonder if there is a C0 neighborhood of the identity such that if your Hamiltonian diffeomorphism is there, then it can be connected to the identity staying inside the neighborhood. And it turns out that this question is extremely difficult, at least I do believe so. So the answer is only known to be actually affirmative when M is an orientable surface, but then there you are in the realm of, area preserving diffeomorphism. So this is mainly due to Albert Fatty's work. And the other case where we know is the symplectic open ball by Sobhan Seyfadini. And as far as I know, it's the only two cases where we can answer this question. So one way to deal with a really hard question would be, I mean, that's what we did, is like find a question which is maybe weaker but still interesting, and let me try to convince you it's weaker and still interesting. So so if you had such a neighborhood of path connectedness, then you will get what I call persistence of intersection via Hamiltonian isotopies, right? So let me explain what I mean and also why it's true. So if you have such a Lagrangian, such a neighborhood of your Lagrangian, in which you know that any other Hamiltonian, any other Lagrangian which is Hamiltonian isotopic to L can be joined to the zero section, I mean, to L by a Hamiltonian isotopy included in this neighborhood, then you can just forget about the rest of the manifold and think of this inside the cotangent bundle of L, right? And then since now you have the zero section and something which is Hamiltonian isotopic to it, then by an old result of Helmut Hofer or François Lodenbach and Jean-Claude Sikov in '82, you know that this other Lagrangian has to intersect the zero section. Or you can even take the generalization, and this is going to become handy later on in the talk. You have this theorem by Gromov, which says that any exact Lagrangian of the cotangent bundle intersects the zero section, right? So in any case, such a Lagrangian should intersect, which means this is a weaker question. You fix a Lagrangian L, and you wonder if there exists a neighborhood such that any Hamiltonian which is Hamiltonian isotopic, any Lagrangian, sorry, L prime, which is Hamiltonian isotopic to L, if it's entirely included in U, then it has to intersect L. Yeah. And actually, that's the first question which was asked to us by Marcelo Atallah, something like 2 years ago. And so if such a U exists, I will call it a neighborhood of persistence of Hamiltonian intersection, or rather a neighborhood of persistence of intersection via Hamiltonian isotopies or diffeomorphism. To tell you the truth, it's the third name I'm trying. The first two didn't convince people. So, if you are not convinced by this one, just tell me. I'll try to find a fourth one. And of course, this question you can also ask with symplectic diffeomorphism, right? You can ask, okay, I have can I find maybe another open set around an open neighborhood of L such that if I have another Lagrangian, which is the image of L by a symplectic diffeomorphism, then it has to intersect, right? And then I would call this new U a neighborhood of persistence of symplectic intersection. So here the question. So let me give you some example which should show that the situation might be a bit subtle. Here, that's my example. It should become more subtle in a few seconds. So it's S1 in C, right? And we all know that by looking at the projection on one axis, then eventually we are going to displace L0 from itself by Hamiltonian diffeomorphism, right? So you do have, yeah, so L is displaceable via Hamiltonian diffeomorphism, right? Now, question is there a neighborhood of persistence of intersection via something? And actually, yes, via symplectic diffeomorphism. For the following reason, it's again an area argument, right? If you try to displace L0 from itself, but staying in a neighborhood of L0, whose symplectic area is smaller than A, the symplectic area of the disk, which is bounded by L0, then you will have intersection, right? You cannot displace it there, right? So of course, then now you have also persistence of intersection via Hamiltonian diffeomorphism. In particular, I mean C, so yeah. But that's the point. If you are a bit careful, if you do this for a very, very small L0, then the thing is you can embed this situation in any double ball and then put this in your favorite symplectic manifold. So here I put that in T2. Right, so let's see another situation where the answer is different. If you take this L1 now, that's another Lagrangian in T2, which is actually very different from the first one because this one is aspherical, right? Pi2 of T2 relative to L1 now is 0. And what's obvious is that the rotation along, let's say, the other obvious generator of pi1 is a symplectomorphism. So L1 can be displaced by symplectomorphism. But it's even worse than that because you can do it instantaneously, right? So somehow you can do it in an arbitrarily small neighborhood of L1, meaning there is no neighborhood of persistence of intersection via symplectic diffeomorphism. On the other side, Fleur tells you that since it's weakly exact, then its Fleur homology is always non-zero. Actually, it's always that of S1, right? So you will always have at least 2 points of intersection. So it's never displaceable by Hamiltonian diffeomorphism, right? So somehow you do have a neighborhood of persistence of intersection via Hamiltonian diffeomorphism, which is the whole manifold. Okay, and now to get something which is in between these cases, you can look at the product of these two. So what is obvious What is obvious? Good question. What's obvious is you can indeed displace it by Hamiltonian diffeomorphism, right? Because you can displace the first factor, right? And also there is no persistence of symplectic intersection because you can displace the second factor instantaneously by symplectic diffeomorphism. And now the question is, does there exist a persistence of, does there exist a neighborhood in which Hamiltonian intersection will persist? And actually, yesterday I prepared the talk and I was like, yeah, of course, because it's yes and yes. I don't see an easy argument to say it's the case, because not all Lagrangians are products, right? So, but in any case, I didn't think about it too much because, in particular, what I'm going to explain later is that for this guy, it's clear that there is a neighborhood of persistence of Hamiltonian intersection here. So these are the examples, and somehow they are really relevant for what is coming because there are several things. So there is this trick of doing things in a small double ball, then you can include it in some manifold. And more importantly, there is a really big difference between L0 and L1. I said that already, but it comes from the nature of the map induced at the level of homology. And here, actually, what will be of interest is H1. By the inclusion of the Lagrangian inside the symplectic manifold. Okay, so this will be again relevant later. Okay, so let me now explain the main results. So the first one is negative result. This we did with Jean-Philippe Chassé in October last year. So we proved that in any symplectic manifold of dimension at least 6, there exists Lagrangian tori whose Hamiltonian orbit have several properties which we didn't expect. So first, it contains arbitrarily closed disjoint elements, and second, is not closed in the set of Lagrangian tori. So I didn't specify the topology here, but it's true for topology you prefer, like C1 topology, Hausdorff topology, and so on. So the first statement obviously shows that there is no nice neighborhood like the one I'm trying to find. There is no neighborhood of persistence of Hamiltonian intersection, hence no neighborhood of persistence of symplectic, and so on. No path connected neighborhood. And the second one is going to disprove something I didn't say yet, but which is going to happen later in the talk about the C0 and C1 Lagrangian version of the flux conjecture. Okay, so another thing I really like with this theorem is that it was apparently extremely inspiring because not even like 4 weeks after I presented this in front of Philippe Brocic and Egor Shelukhin, they got inspiration for another construction of Lagrangian disproving the Lagrangian Poincaré recurrence, which I think is really nice. And then really not much later, so yeah, one thing which is important, and that this theorem by Jean-Philippe and myself works in dimension greater or equal than 6, right? And in particular, our proof does not work in dimension 4, and we were wondering if it was true in dimension 4, and it's the same. Actually, there were examples found out really soon after by Schmitz in dimension 4, and I think he also disproves the Lagrangian Poincaré recurrence with these examples. And then a few weeks later, there was other examples by Brendel and Kim. So this time they don't disprove the Lagrangian Poincaré recurrence, but they do also have this tori with Lagrangian tori with nasty topology, with this type of properties, right? And it's really nice. Their method is completely different. Like they manage to characterize the Hamiltonian isotopy of split tori in non-monotonous 2 times S2 by viewing this problem as a billiard problem. I think it's really nice also. So anyway, all of this is related. And one last remark, which is really important, even if technical, it's like the tori we construct are not rational, right? So the group of relative period, the image of pi2 of m relative to L via omega, is not discrete. So actually, this is going to be really important. So let me give you the actual condition we need. We need a variant of this. We are going to work with a rationality condition, which is an homological variant, right? So that's the H. We say that L is H rational, like homologically rational, if the group, I mean, the image via omega of H2 of M relative to L is discrete. That is, it can be written tau Z for some non-negative tau. And we're going to say that in that case, if tau is 0, then L is H exact. So this will be, and then we can already, if we think of the examples we have, this, at least in general, this is going to be essential condition. We have another condition, but this one is not, I think, essential. This one comes from the methods we use to prove our theorems. It's almost only topological, except it's not. So I needed a name for this condition, so I call this condition curly C. Sorry, it's just a name. So we're going to say that L satisfies C if either H1 is 0 or with real coefficient. H1 is of dimension 1, but then you need to know that there exists, like the abstract manifold L admits also a Lagrangian embedding inside a Liouville domain with vanishing symplectic homology, or L is a product of the above cases, or you know that L is covered by one of the above cases. So these are all the conditions, all the cases where we can actually prove positive results, which appear now, right? So this appeared in January with Marcelo, Jean-Philippe, and Egor. So the positive result is the following. If L is a H rational Lagrangian satisfying C, right? So both conditions I just presented, both are satisfied. Then L admits a neighborhood of persistence of Hamiltonian intersection and period. You don't need anything else. And then we have two moreovers, which are independent, right? So on one direction, if you happen to know that, I told you this map would be important, that if you happen to know that the inclusion of L inside M induces the zero map at the level of H1 with real coefficients, then you can also say that L admits a neighborhood of persistence of symplectic intersection. And you will see the reason behind, which is kind of obvious, but then I cannot explain it now. And the second one is if you happen to know that the nearby Lagrangian conjecture holds in T star L, then you know that L admits a neighborhood of Hamiltonian path connectedness, like positive answer to question A here. So that's what we have, and we have a lot of really natural examples. So for example, S1, yeah, S1 can be admits a Lagrangian embedding inside the compact disk in C, which is a Liouville domain with a symplectic homology 0. So S1 works, and then you can do products. So for example, you immediately get Tn times Q with Q as zero first homology group with real coefficients, right? So for example, S1 times Sn in Cn plus 1, that's an example which fits there. We also have Klein bottles because of the covering property. Actually, for Klein bottles, we also have an ad hoc proof, which is really nice, and it's based on the non-existence of Lagrangian Klein bottles in C2, which is a deep result by Nemirovsky and Shevchin. And then we have plenty other examples which are a bit more weird in some sense, right? If you want a weird example, for example, something funny, you take a finite family of three-dimensional length spaces, and you connect some them together, and you connect some this to S1 times S2. So you get a three-dimensional manifold, and then by a theorem by Ekholm, Eliashberg, Murphy, and Smith, you know that this actually has a Lagrangian embedding inside C3, so you can still apply the theorem. And if you want even weirder, just to take products of these things, but I mean, okay, sorry, that's why I just wrote dot, dot, dot. Okay, and for the last thing, sorry, neighborhood of path connectedness. So yes, okay, it's kind of a pity we need the nearby Lagrangian conjecture, but you know, I'm a complete believer of that. I think it's true in great generality, so it's not that bad for me. And still, we still have really nice example, right? So for example, you take any H rational two-dimensional torus in C2, S2 times S2, CP2 blowups, and then you know that it admits this type of Lagrangians because so we know that the nearby Lagrangian conjecture holds thanks to Dimitrov, Glorisel, Goodman, and Ivry. And the same if you replace T2 by S2, thanks to Richard Hein, right? And then also RP2. So this was a result by Hein, Pinsonneau, and Vu, and with a new proof by Adaloglu. Here. Okay. So how do we prove this? I mean, if you thought about this question a bit, there's something which is clear and which actually which goes back to Gromov, and that's what I explained earlier, right? If you can prove that for your H rational Lagrangian satisfying this condition, then you have a neighborhood of these guys such that the Lagrangian which are of interest for you, so for example, Hamiltonian images of the initial guy, then if you happen to know that this guy is exact, when you see this via Weinstein's symplectomorphism inside a neighborhood of the zero section in T star L, then you're done, because then you have intersection with the zero section, and if the nearby Lagrangian conjecture hold, then you know that you have, Hamiltonian isotopy inside the neighborhood, right? So you might think that's how we prove it, and that's actually what we do. We prove it like this. And then to prove exactness of nearby Lagrangians, we do it in two steps. The first step will be a theorem. So you take L, which is the H rational Lagrangian. And for this first step, that's the one where we need this topological / symplectic additional condition. So assume that L satisfies this condition, then I can tell you that there exists a Weinstein neighborhood such that if you take in the initial manifold, you take the image of L prime by some other, by some symplectic diffeomorphism, right? Then if this L prime is entirely contained in W, then L prime is H exact in W. Okay, cool. And now we have a second theorem, which is somehow where it's more general in the sense that we don't need this additional condition, is that if you take L again, there exists a neighborhood which might be smaller, bigger, I don't know, which with the following property: if L prime is H exact in this neighborhood, when you look at it inside the cotangent bundle, then actually the image is exact, right? So we have exactly what we want, right? And this holds for any without additional assumption for any L prime which is Hamiltonian isotopy to L, and it's actually true for any L prime which is the image of L by a symplectomorphism, if you happen to know that the inclusion of L inside M induces the zero map in H1 with real coefficients, right? So it's clear that these two theorems together tells you that exactly the guys you want are going to be exact, hence the conclusion of this theorem, right? So these theorems are what you need to prove the one I explained before, right? But actually we prove more. We prove something which is more general. So let me, and actually it's going to be used in the rest, like for the application. So I'm going to explain just a little bit, but then I need a new set of Lagrangians, right? Is this curly L of L tau? So tau is a real number, and then curly L is the set of Lagrangians which have the same diffeomorphism type as L, which is the first parameter, which are H rational and with fixed H rationality constant tau. Okay, I hope it's clear. So in particular, is tau is the H rationality constant of L. L is obviously an element of this set. And what we prove is that we can replace the symplectic orbit of L by actually the set of Lagrangians, which are the same diffeomorphism type of L, which are H rational with the fixed H rationality constant, but which doesn't have to be that of L, funnily. So if you want to write a proper, like a really precise statement now, so you assume that L satisfies this symplectic this topological symplectic condition C, and then for any H rationality constant tau prime, which is fixed, there exists a neighborhood, a Weinstein neighborhood of L, which now depends on tau prime, obviously, such that for all L prime, which are tau prime H rational, if they're inside W, then they are H exact. And we also have some type of improvement of the second theorem. For some reason, it's really funny because we don't need to assume that the Lagrangian L prime has the same diffeomorphism type as L, but now we are stuck. We cannot. We need to assume that it has the same H rationality constant anyway. So this theorem will come back at the end. I will give you elements of proof of these guys. But this is what we prove actually. Oh, and yeah, that's why that's another reason why I insisted on that. So if you look at the second theorem, with the blue variant, right? Actually, that's one reason why we use homological exactness. I mean, homological rationality and homological exactness. This theorem is not true if you replace H exact, like, which is orange now. If you replace this assumption by just exact or weakly exact, I don't know what we should say. Yeah, sorry, not exact. Exact doesn't mean anything. If you replace H exact by weakly exact, meaning that omega vanishes on pi 2 of W comma L prime, then this is not true. And you have counterexample which come from a work of Leonid in 1993. So in particular, it proves. So one example is you take a Klein bottle. You take a Klein bottle, and what you can say is that in the cotangent bundle of the Klein bottle, arbitrarily close to the zero section, you have Lagrangians, which are weakly exact, but not exact here, right? So that's one reason why we use this is kind of homological variant of exactness here. So these are the main steps of the proof. So let me mention applications. Application. So the first, I mean, the most, I don't know, to me, the most interesting are toward the Lagrangian flux conjectures. So let me recall what it is because it's really natural, super easy, and really, really nice. So the flux conjecture, right? Everything becomes started with the flux morphism. So how do you define this? You take a loop in M and an isotopy of symplectic diffeomorphism starting at the identity, and you feed the loop to this isotopy, you get a cylinder. This cylinder, you extract the area of its, the symplectic area of this cylinder, and what you just did is like to a loop in M and an isotopy of symplectomorphism, you got a real number. The thing is, just using Stokes' theorem twice, like once in both cases, you can see that this only depends on the homotopy class of the loop in M and also of the homotopy class with fixed ends of the isotopy. So what you actually did is you defined for an element of the universal cover of Sim0, you define a morphism from pi 1 of Am to R, which is exactly the first de Ham cohomology group as I wrote it down. So now what you can do is you can look at the image of the fiber on top of the identity, which is like pi 1 of Sim0, right? And this is called the flux group. And the conjecture was that this group was discrete. And now it's a theorem, right? It was proven by Kaoru Ono in 06. Amazing theorem. Okay, gamma is discrete for, I mean, in full generality. This is crazy. And this was called the C1 flux conjecture because it was known that it's equivalent to the fact that Ham is C1 closed in simp. So as soon as you wrote Ham is C1 closed in simp, you can wonder, like, we like C0 symplectic geometry, we like, I mean, it's not even that, it's like you want to understand, topological, the topological properties of these spaces. So as soon as you wrote this, you wonder, like, is Ham C0 closed in simp also? So I don't think there is any interpretation in terms of flux group or things like this, but at least, yeah, it's a question you can ask. And this question, so the C1 flux conjecture has been proven in full generality, and C0 is widely open. So as far as I know, there is this initial work of François Lalonde, Dusan MacDuff, and Leonid Poitovich in '98, improved a bit later, yeah, 20 years later, by Lev Byovsky. Okay, and so, okay, you can wonder, like, what about Lagrangian variants? And actually, this was already considered, right, by Ono in 2008 and by Solomon in 13. And one way to write it down is this way. So we are going to use exactly the same definition, loop, an isotopy, area of what you get, but now things change a little bit, right? The loop will be in L, sorry. And the isotopy, yeah, will come from this set which I defined at the beginning but didn't use to, I recall the definition, like the orange set. These are the Lagrangian, which are isotopic to L via Lagrangian isotopies, right? So you take a Lagrangian isotopy, you take a loop in L, you look at the cylinder, omega, and so on. And then this gives you a map from the universal cover of this orange set to the first Durham group of L, and you can look at the image of by one of the guy. Okay, and then, right, the question is the Hamiltonian orbit and the symplectic orbit C1 close in this, or can we say something on the discreteness of this guy? Right, so, and the first theorem we proved, the second point of the first theorem tells exactly this, is that this is not going to work in full generality. That is, in any at least six-dimensional symplectic manifold, there exists Lagrangian tori such that this flux set here is not discrete. And also, we proved that the Hamiltonian orbit is not Hausdorff closed in lag, in the set of Lagrangian, which can be obtained from L via Lagrangian isotopy. Yeah. On the positive side, what we prove with the four of us is that if L is H rational, and then and that's all. Actually, for the C1 version, it's all we need. If L is H rational, the Hamiltonian orbit and the symplectic orbit are C1 closed in the set. Another set. So this L of L here is just the set of Lagrangian, which has the same diffeomorphism type as L, right? If on top of this, you do have the topological symplectic condition C I mentioned, so we can use the theorem we have. And if you happen to know that the nearby Lagrangian conjecture holds in T star L, then the same holds in Hausdorff topology. So here are four positive results. And let me compare with the results that pre-existed. So first, it's not comparable with Ono's result. I mean, the intersection. I mean, it's completely orthogonal. We don't have the same condition to prove this, so that's nice. But what I wrote for the C1 version is completely included in Jake Solomon's results in 2013, except that he requires the symplectic manifold to be closed, and we don't. So, okay, that's a difference. Yet, the Hausdorff version, as far as we know, is new. And for example, it holds for H rational 2 tori or 2 spheres or P2s in C2, S2 times S2, CP2 blowups, and so on. Okay. So more on the topology of this type of sets, we wondered about closedness. What about openness? And actually, we can prove this. if L is H rational with constant tau, then the symplectic orbit is C1 open in the set of Lagrangians, which are of diffeomorphism type L and the same tau H rationality constant. And again, if you have the symplectic slash topological condition and you know the NLC holds, then the same holds in Hausdorff topology. Which is quite nice is that somehow this proves that the symplectic orbit is open and closed. And so you get that the path connected components of this set are of the form symplectic orbits of Lagrangian, right? And so one example, which is fun, probably it was known before, but not by me, but I don't know. When they proved the nearby Lagrangian conjecture, Dimitroglou, Rizal, Gunman, Ivry, they also show that the monotone Clifford torus and the Chekhanov torus are Lagrangian isotopic. Sorry, or Lagrangian isotopic, but not symplectically isotopic, right? And so with what I wrote before, it proves that they belong to different connected components of the space of two tori, which are tau H rational. Or if you will, if you go by a continuous path from one to the other, then you need to leave this space here. Oh, and then the last corollary, and this is what I quickly mentioned, actually, this openness you can also prove for the Hamiltonian orbit, the theorem on top of this slide. You can prove for the Hamiltonian orbit if you assume that, again, the Lagrangian vanishes at the level of H1. I mean, the inclusion of L inside M induces the zero map at the level of H1 with real coefficients, which means that actually these guys are also open and closed, and this means that actually the symplectic orbit and the Hamiltonian orbit are the same. So somehow you should think of this theorem as the Lagrangian variant of if H1 of M is 0, then Sim0 is equal to M. Okay. And I have one last, do I have time? I think I do, right? Yes. One last really quick application is this thing. It's C0 rigidity of Hamiltonian diffeomorphism. So you take L, which is displaceable. I want to displace it, so it needs to be displaceable. And you assume it's H rational. Then what we're saying is that there exists some constant delta, which is positive, such that any Hamiltonian diffeomorphism which displaces L is at C0 distance from the identity at least delta, which I don't know, was not known. Actually, it's known to not hold for non-Lagrangian half-dimensional submanifolds, right? That's a consequence of Lodenbach and Sikorov's theorem. And on the other side, if you know the spectral distance, there is a way to prove this quickly in your head, thinking like, yeah, oh no, I can use the fact that spectral displacement is non-degenerate, like it's positive. And so when gamma is known to be continuous, C0 continuous, then you can prove the same thing. And you can do this in more and more spaces, but it's not yet completely general here. So now I'm going to give you ideas of the proofs, except if there are questions, or I'm not checking, right? So, okay, elements of proof. So let's start with the first theorem, which is the irrational counterexamples. So I recall the theorem here, dimension, symplectic manifold dimension at least 6, then Hamiltonian orbit with arbitrarily closed and disjoint elements, first point, and it's not closed in the set of Lagrangian tori. And the main ingredient here is just this amazing Chekhanov's classification of Hamiltonian isotopies of split tori in Cn. Not even Cn actually, in C3. So what happens in C3? So we fix a product torus, which I called L1 alpha, right? So it's the product of S1 of capacity 1 times S1 of capacity 2, which I wrote 1 plus 1 so that what happens later is more clear, times S1 of capacity 1 plus alpha for some alpha, which is a real number. And then Chekhanov's classification tells you that any other Lagrangian, which is split and of the form S1 of capacity 1 times S1 of capacity 1 plus A times S1 of capacity 1 plus B, with A and B positive, will be in the Hamiltonian orbit of L1 alpha, the initial guy, if and only if the set of real numbers you can get, like the set of real numbers generated by A and B over the integers, right? So the set MA plus NB for Mn integers is the same as the set generated by 1 and alpha over the integers. So that's really nice. And what we did is to remark that actually, if alpha is not rational, then the set of pairs AB, no, so the set of pairs of positive elements such that we do generate over Z the correct set is dense in the set of pairs of positive elements, right? So when you have this, then you can produce all kind of weird thing, right? Assume, take a sequence of A and Bn, which are in this set, and which converge to 1 alpha. Then what do you get? You get a sequence of tori, which you can assume are all disjoint, because it's just taking A and Bn different from A, K, Bk for any n and k. This you can always do. Which are all in, so they are all disjoint, they are all in the Hamiltonian orbit, and they converge to L1 alpha. So this gives you the first point already. You can take another sequence, A and Bn, which converge to 0, 0, for example. And now you get what? You get split tori, which are all in the Hamiltonian orbit of the first guy, the initial guy, and they converge to the Clifford torus S1, 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 right? Which cannot be in the Hamiltonian orbit because it's monotone, right? And the other one is not even H rational. So here you prove the second point. So this proves the theorem in C3. Okay, we don't want C3, we want M6, at least 6. So first you go from C3 to Cn by multiplying by some, not necessarily stupid, but standard torus, S1 of capacity 1 times S1 of capacity 1 times and so on, n minus 3 times. And then you want to do exactly what I did at the very beginning, like with my two circles, saying I can do this in a small neighborhood and then embed this anywhere. And actually, you could do that if you had a theorem saying that all the isotopies you need to go from LAB to L1 alpha, they can be realized in a ball of size controlled, right? And that's exactly the theorem that Chekhanov and Schlenk proved 20 years after Chekhanov's classification, that all these isotopies can be realized in a uniformly bounded ball. So you take things small enough, the ball is small enough, you put this in a double ball, and you embed this in any manifold of dimension at least 6. Here, this is the proof. There is no question. I can give you more details about the second theorem. So the second theorem is the neighborhood of H-exactness, right? So I wrote the theorem there. So L is H rational, and it's I wrote tau for its constant. It satisfies the condition C, like the symplectic topological condition. And I'm saying for any other tau prime, there exists a neighborhood which depends on tau prime, such that for any Lagrangian, which is H rational with constant tau prime, if L prime is inside W, then it's H exact in W. So let me just recall the condition. That was symplectic condition, right? Remember, H1 is 0, H1 is R, but then you need to know that L embeds in some Liouville domain, or L is a product of this guy, or L is covered by one of these above. So H1, 0 is kind of not so... I mean, I'm going to explain the proof in this case because it contains all the ingredients to understand what's really happening, right? So I will assume that H1 of L is with real coefficient is of dimension 1, and that you do have this Lagrangian embedding. So the proof is based on variance of Chilibach-Monke's symplectic capacities, which is a min-max, right? So let me give you our variant. Actually, there are 3 variants, but they all look like this. It's a min-max. Let's look at the mean. So I wrote a mean for what? The infimum of the positive symplectic areas of element in relative H2, right? H2 of X, which is the symplectic manifold. I don't know why it's called X now and not M. Relative to L, and L is going to be a Lagrangian, right? And you do the supremum of this quantity over Lagrangians in this curly L now, a new curly L. So what is this? Actually, we have three such capacities because we have three such families of Lagrangians. This is not going to be important in anything which follows, but I just want to explain roughly, right? So that L is going to be a Lagrangian in X omega in your symplectic manifold, which is the same diffeomorphism type as Q, right? It's the image of an embedding, a Lagrangian embedding, right? And now we have three conditions which are stronger and stronger. The first one, which is the weakest, is the weakest condition you can ask so that your definition makes sense. Like otherwise, our A mean on top might be plus infinity, and then, you know, the supremum of something now is not really interesting. So somehow you need to assume at least that. We tried with Jean-Philippe in the first version of the paper to prove stuff with a capacity which was equal to a plus infinity, and it's much, much harder. We couldn't do it. So now we have a condition which is stronger, which is that the map, the embedding from Q to H, to X, sorry, is not surjective at the level of H1 with real coefficients. And we have a strongest condition saying that this map actually vanishes. So funnily enough, since I am in the setting where H1 with real coefficient is of dimension 1, all of these families are the same, so all the invariants are the same, and I just call it CQ. Okay? So I'm saying this is a capacity, and it's quite not a capacity in the sense of symplectic capacities. In particular, it doesn't have all the properties needed for the axiomatic definition of symplectic capacities, but it has some which are going to be sufficient for us. Yay! The first one is scaling, right? The one you expect. It's like if you multiply the symplectic form by a constant alpha, then the capacity is going to be multiplied by absolute value of alpha. Excellent. Then it has a partial version of monotonicity. So remember, monotonicity is what I wrote in orange here. If you have a symplectic embedding of M inside M prime, then the capacity of M is smaller than the capacity of M prime. Makes sense? Really nice definition. I mean, that's really nice property you could expect. So here, this is not going to be the case at all, but we have a partial version. So the first thing is we don't have this capacity of M smaller than the capacity of M prime is going to be smaller than B, and B is some integer times CQ of M prime, but this is not really, this is absolutely not a problem because B only depends on like the torsion part of H1 of M with the coefficient. So somehow in our proof, you will see, since we do this for cotangent bundles of different size of one fixed Lagrangian, this is fixed and we don't care, so that's perfectly fine. More annoying, it doesn't work for any symplectic embedding, but it makes sense. It works only for codimension 0 symplectic embeddings, but obviously, I mean, we want to compare Lagrangians in M and Lagrangian in M prime. So, I mean, if the dimension goes up, what do you want to say, right? So this makes complete sense, and it will be still enough. And also, it will work, at least the version I'm presenting now, will work if M prime is exact. Yeah. So okay, let's work with this. So remember, I took L to be Lagrangianly embeddable inside some Liouville domain. So this Lagrangian embedding induces a codimension 0 embedding of a small neighborhood of the 0 section in the cotangent bundle of L inside W. So you get this symplectic codimension 0 symplectic embedding inside W for some positive radius. So this, and also I said W is with symplectic homology 0. So this then you can use, and you invoke this huge, I mean, this deep result by Zhu, saying that then you know that this capacity which I wrote C all of W is finite. So what is C all? It's obviously, I mean, tautologically greater than CL of W. This is just the supremum of our capacity CL over all diffeomorphism types of L, right? So it's, if you will, it's a sup over all possible Q of CQ of XW. So Zhu says, yeah, this is finite, so the capacity of W is finite. Okay, great. Now, what can we do? Now, by monotonicity, we know that the capacity of this small neighborhood of the zero section in T star L is also finite. Excellent. But then, by using scaling, and also actually, but it's really not important, monotonicity, you can show that then if you take smaller and smaller neighborhood, you take neighborhood of size r with r going to 0, then actually now not only is finite your capacity, but it goes to 0. But on the other side, if you have a Lagrangian which is H rational but not H exact in any of these small neighborhood, then its capacity has to be greater than tau prime. It's like by definition, right? So it has to go to 0 and be bigger than tau prime contradiction. You're done. So what is really important in this proof is that once you're given these capacities with their properties, the only thing you need to prove is that the capacity is bounded. Okay, that's really the thing which is behind the proof, and actually this has a really nice interpretation, right? So the fact that there exists a neighborhood of the zero section for which this capacity is bounded is equivalent to the following the following Lipschitz property of the rationality constant, right? So I wrote it down. So you see that I should have wrote it down the other way. I'm sorry. There exists some constant C such that for all H rational Lagrangian in your neighborhood, right? So you take a neighborhood of size R, and then all H rational Lagrangian in this neighborhood, for which the canonical projection is not surjective, will have H rational constant smaller than C times R. It's some type of Viterbo conjecture for the rationality constant. And so actually what this argument proves, like with the scaling and the thing, is just that actually if L satisfies our symplectic / topological condition, then we do have Lipschitz behavior of the rationality constant here. So this is the proof of the second theorem, and if you are okay with that, I will give you elements of the proof of third theorem. So the third theorem was going from H-exactness to exactness, right? We have this H-rational Lagrangian again, and then I'm saying there exists a Weinstein neighborhood such that if the Lagrangian you're interested in are there and they are H-exact, then when you see this situation inside the cotangent bundle by Weinstein's symplectomorphism, then they're actually exact. This proof was given to us, actually. It was sketched in a paper by Cédric Membrez and Emmanuel Epstein from 2021. So it's based on ideas of Paternane, Polterich, and Seeberg. So if you go through the proof, so what they do, they give you an inequality as the one is written in the middle of the slide right now, and which I'm going to explain in 1 minute, right? But the thing is, if you go through their proof, you realize that you can relax a bit the assumptions. All you need is for your Lagrangian L prime to be, I don't remember exactly, but that there exists a symplectic isotopy. So you're in the cotangent bundle, right? So there exists a symplectic isotopy which preserves the fibers and which sends this L prime to some other Lagrangian, which is going to be exact and admits graph selectors. And the thing is, later on, this second condition fell down by itself because Amorim O. dos Santos, with Fleur theoretic arguments, and Stéphane Guillermo with Schiff arguments, proved that actually any exact Lagrangian in the cotangent bundle do admit graph selectors. So, tada, what we can prove is the following. If L prime is H exact, so we can prove that if an H-exact Lagrangian in the cotangent bundle indeed admits this symplectic isotopy, which so we can apply the result of Paternane, Polterich, and Seeberg. So what does it say? I'm explaining the inequality now. So you see, it's valid for any class in H1 of L prime. And it will give you not lower, the other one, upper bound of the value of the Liouville class on this homotopy class. And the first thing you do is you take your beta prime and you send it to the first homology group of L by using this orange pie, like the canonical projection, right? It's just L prime included in the cotangent bundle, canonically projected to L. So now you have a class pi star B prime inside H1 of L. And what's going to be the bound? It's, okay, the size of the neighborhood times this quantity, which is the minimal length of a geodesic in the class pi star of beta prime for some metric G, which is fixed beforehand, right? So, and this is awesome because you are in H1 of L, so it doesn't depend on L prime anymore. So it's super easy to just bound that independently of L prime. And then what you get is that beta prime for any H1 even L prime, I mean, lambda of beta, so the image of H1 of L prime by lambda is smaller than R times some constant, which does not depend on L prime. And again, same type of things as before. If L is H rational in M with constant tau, and L prime is also H rational with constant tau, and L prime is inside this neighborhood of L, which you want to see now in the cotangent bundle, you can prove, it's not hard, that the image of the Liouville form on H1 of L prime it's not actually tau z exactly. It's included in tau divided by k, sorry, which is an integer, a natural integer, times z, right? Where k, so remember, either you want to prove this for Hamiltonian perturbation of L, and then you can take safely k is equal to 1, or you want to take it in a much more general family, but then you know that the inclusion of L inside M vanishes at the level of H1 with real coefficients. This gives you exactly, by some usual, algebraic topology, long exact sequence stuff, that the co-kernel of the map from H2 of M relative to L to H1 of L is non-trivial, and you can take K as the size of this co-kernel. And then it's done again, because if R is small enough, then it's smaller than, I mean, R times the constant we had above is smaller than tau divided by K, and then lambda of H1 has to be 0. It's exact. Thank you. And I'm done. Oh, sorry.
Any questions?
I have a question actually about this last argument. Are
Excellent.
you assuming here your condition C or whatever? C? In this last slide?
Not in this, no, not in this slide. This result here is completely general.
But
The condition
H-exactness,
C, I mean, you see, the condition C we use to use the Chili-Bach-Monkers type invariants, right? So that's for the other theorem.
sure. And H-exactness is said every sort of surface with boundary on the Lagrangian has 0 symplectic area.
H-exactness, yes, exactly, yeah.
Interesting. Okay, thank you. I guess I have another question. Can you show me again this list of Lagrangians? It was like a circle, product of two things, the embedding into the thing. Is this it?
Yes.
Yeah. I see. I see. Yeah.
Yes. And the thing is that for H1 is equal to 0, okay, so things are kind of magically working out by themselves because you don't have H1, right? For H1 of dimension 1 plus this Lagrangian embedding I kind of explained. And the thing is, this theorem here, sorry, the thing that, yeah, this one, like the property, the Lipschitz type property actually goes super well with products and with coverings. Like it's really easy. I mean, it's really you can show that if actually, yeah, this property you can show that if two Lagrangian have this sorry, you can show that if L and L prime have this property, then L times L prime has this property, and then if something covers that, it has the same property. That's so that's
Interesting. What about this? So if I take a circle in the cotangent bundle, slightly sort of shifted up from the 0 section.
So you're in T star S1 or?
Yeah, T star S1. And I take a circle, I slightly shift it up off the 0 section. Now it seems like it's H exact, but it's not exact.
No, but this guy will not be. Sorry, you're saying that this should disprove.
No, I
I'm
don't
not
think
sure.
it disproves
I
anything.
know it doesn't disprove, but so what are you asking? Sorry, I didn't get that. So I'm looking at T star S1 and I shift a little bit the 0 section. Yeah, by symplectic. Yeah. Okay. So what?
Well, it's H exact, but it's not exact, right?
Exactly. Yeah.
It's H rational. No, it's H exact, but it's not exact. So I see. But it fails this like map on H1 to the 0.
Exactly. Yeah. The map on S1 is not. So actually, the thing here is that the map on S1 is. I mean, the canonical projection gives you an isomorphism from on the homology of these two guys, right? So that's.
I see. I see. Very interesting. Okay, thank you. Sorry for the very strange question, but I was just a bit confused about that. But okay.
Rémi, what is the easiest example of a Lagrangian for which you cannot decide?
At the very beginning, yeah, maybe there is an obvious argument I overlooked. This one, like the product? Felix? I cannot hear you anymore.
Me?
No, Felix. I can hear you, Dylan, but I cannot hear Felix.
It's not decided. You can hear or not?
Yes, now I can hear you. Can you repeat, please?
Can you describe the easiest class of examples where you do not know whether you have this persistence of intersection or whether you can disjointly pack any neighborhood?
But then you just need to, okay, wait one second. So for the Hamiltonian intersection, so for example, I mean, if you have a Lagrangian which doesn't satisfy my assumption C, like right, then I don't know. Is that what you're asking, or?
So what would the easiest concrete example be? Already on surface or on dimension or like 2?
It should be easy, right, to find something which does not satisfy this. Sorry. I don't know, like yeah, for example, Lagrangian of the form. No, it has H10. Oh, come on. should be easy to find a manifold which is not which does not fall in this.
But an easy one where you can maybe use other tools.
Well, you could have something irrational already. So if you want really easy, you have something that's right. I mean, irrational is not so
Yes.
hard to produce, right?
No, and then it's easy, but then irrational, you might be in a case. I would think that, I mean, except in dimension 4, where I think that, for example, for even, except for dimension 4, what do I want to say? I think irrational, you should not waste too much time to prove that you do have persistence of Hamiltonian intersection, because that's where we construct the examples where you don't.
Yeah. Well.
If I think Felix is looking for the next
where you cannot decide, where you are in between. Yeah, I see.
Yeah,
I
exactly.
It was not told where you read or no.
Yeah, I understand.
Yeah. No, I think there are plenty of manifolds which do not fit in this condition C, but now I'm lacking the imagination. I'm sorry. That's ridiculous.
Well, I guess there's lots in condition C, but you know, they are not displaceable usually, right? So there's a surface with.
Yeah, also, yeah, if you take something
Genus,
that's
I can't
topologically
displace.
displaceable, yeah, exactly. Yeah. That's a good. That's not really interesting. Yeah.
Okay, so if there are no further questions, let's thank Rémi again.